when the similar groups or same groups are at the same side of the double bond, to minimize the repulsion, they will become out of plane perpendicular to each other. If I just place one mirror in front of this molecule. Hello students, welcome to Allen Overseas and welcome back to our very special series, that is 45 important topics in 45 days, that is important for your JEE Main 2024, right? And we have divided this series in 3 parts. 15 topics of physics, 15 from chemistry and 15 from mathematics, and I will be discussing this chemistry part, right? So we are going to continue with our next topic from chemistry, and that is very important, is stereo-isomerism, that is taken from the chapter isomerism, right? As you know, this is a very important topic from chemistry. So now let's see. First of all, we will see what is stereo-isomerism, what are stereoisomers. Okay, so as we all know that isomers are those compounds which are having same molecular formula but different structure. But in isomers also, if we talk about this particular category, stereoisomers, then they are also isomers, means they are also having same molecular formula. Even their structural formula is also same. So they are having same molecular formula and same structural formula, but the arrangement of atoms or groups in the space, that will be different. Okay, that's why we call them as stereoisomers. So molecular formula is same. Structural formula means the connectivity of atoms is same, right? But the arrangement of atoms and groups in the space is different, right? And here, if we talk about how many types of stereoisomers we have 2 types of stereoisomers, basically geometrical isomerism, and other is optical isomerism or optical isomers, right? So let's start with the geometrical isomers. Geometrical isomers are those stereoisomers which are obtained due to different orientation of atoms or groups in the space around restricted rotation, are called as GI or geometrical isomers. Okay, so basically here you can see this word restricted rotation. First of all, these are stereoisomers, so they have same molecular formula, same structural formula, but the arrangement or orientation of groups or atoms is different, and that is different due to some restricted rotation. That means the bond cannot rotate freely. We know that single bonds rotate freely, but the double bond, triple bond and the ring, they cannot rotate freely. So if they cannot rotate freely, that means the rotation is restricted. Okay, so restricted rotation is the necessary condition for geometrical isomerism, right? So if we talk about the conditions which are required for the GI, so first condition is restricted rotation must be present. Okay, this is very necessary condition, and this restricted rotation can be due to double bond, triple bond, or ring. Okay, double bond, triple bond or ring. But yes, this restricted rotation can be due to the triple bond also. But one thing we should remember that yes, triple bond has restricted rotation, but triple bond, these compounds which are having triple bond, around triple bond the GI is not possible, because this will not follow the other 2 conditions. Okay, so that's why we can mark it and remove it from the GI. Okay, no GI for triple bond, because it is having restricted rotation, but the other conditions will not be followed. How? Let's see. The two groups at each end of restricted bond must be different. Okay, how? If I talk about the triple bond, then suppose this carbon are having triple bond. Now there are no there is only one bond. There is only one free valency for these carbons, one free valency for these carbons, okay, and this is already linear. So I cannot change the orientation, whatever atoms are present here, A or B, I cannot change their orientation in the space, okay. That's why the second condition is not applicable for the triple bond, so that's why we cannot take it. So, but yes, we can take the double bond. For example, suppose you have this double bond, carbon-carbon double bond, and it is saying that the two groups at each end there should be two groups. So, suppose I have this A group, okay, and this B group, okay, at one carbon at one end. So, it is saying that the two groups at each end of restricted bond must be different. Must be different means, like if this is A and B, so here also we should have A and B. It should not be like A and A. If at this one end, I have different groups and atoms A and B, but at the other end I have same atoms or groups, okay. So in this condition, no GI will be possible. In this condition, no GI will be possible, no geometrical isomers, because the two groups at one end are same, okay. This should not be there. The groups should be different, okay. Now, if we talk about the third condition, that is terminal valency should be present in the same plane. So the terminal ends, the terminals, they should be present in the same plane. It should not be the condition like one end, the atoms present at one end are suppose in this horizontal plane, and suppose the other end atoms are vertical. So they should not be perpendicular or in different planes, okay. If the ends, if the terminal atoms or groups are present in different planes, then GI will not be possible, okay. Like in this case that we have seen for the double bond. So this compound having double bond and the groups at the end are also different. So it is following first condition, restricted rotation. Second condition, the groups at the end are different. And the third, okay, the third is terminal valency. They should be in same plane. So we know that this carbon is sp2. This is also sp2. So these all atoms are present in the same plane, okay. So it is following all the conditions required to show GI. That's why this compound can show geometrical isomerism. And how it can show? When the similar groups or same groups are at the same side of the double bond, then such geometrical isomer is called as cis isomer, okay. On the other hand, when these are the same group or atoms are at opposite side of the double bond, like one B is here, but second B is opposite. Similarly, A and A, they are opposite. So in this condition, this geometrical isomer will be called as trans geometrical isomer, okay. So cis and trans, this is one example of geometrical isomerism. Now let's see this question and try to find out that which compound will show geometrical isomerism, okay. So let's see. Okay, here first compound. Here in the first compound you have the rings. In the first and second compound you can see that we have four membered rings directly connected to each other continuously, okay. So this situation is actually equivalent to allenes. If you remember the case of allene, CH2 double bond C double bond CH2. This is the simplest allene. Allenes are the organic compounds which are having cumulative double bonds like this, okay. So this is the simplest allene, and we know in allenes we have two cases. In allenes we have two cases. When allenes are having even number of double bonds, even number of double bonds, okay. In this case, when allenes are having even number of double bonds, the terminals are not in the same plane. Terminals are not in same plane, okay. And the other case will be when allenes are having odd number of double bonds. Odd number of double bonds. In this case, the terminals will be will be in same plane, okay. So that's why these allenes are very important to find the geometrical isomer and to discuss about the geometrical isomerism, right? So here these compounds which are having the rings here are equivalent to the double bond. So the same conditions that we follow for the allenes, we can follow for such kind of compounds also which are having the rings, right? So here you can see you have two, that is even number of rings, that is equivalent to even number of double bond in allene. So that means they will be present in different planes. So if one is vertical, the other will be horizontal, right? So they are perpendicular. So their ends will also be perpendicular to each other. So that's why here no GI is possible. No GI, okay? No geometrical isomerism here for the first compound. For the second compound, you have odd number of rings. Odd number of rings equivalent to odd number of double bonds in allenes. So that means we can say if this is vertical, this will be horizontal and this will again vertical. So the terminals have come in the same plane, right? So here you have one methyl and the other is hydrogen. One methyl and other is hydrogen. So with respect to methyl and hydrogen, we can make the geometrical isomer cis and trans. When both methyls are at the same side, cis. When they are opposite, it will be trans. So yes, this compound can show geometrical isomerism. GI is present here. Okay. Now the third example, if you see, this is a triphenyl compound. Triphenyl compound, okay. So in triphenyl compound, although we know that there is a single bond between two phenyl rings, so single bond can rotate freely, just like this, okay. Free rotation is possible, but when you will see the middle ring here, you can see you have four methyls, and here also you have methyl and bromine. These are bulky groups. Methyl and bromine, these are bulky groups. So due to these bulky groups which are present on the middle phenyl as well as in these terminal phenyls, so due to these bulky groups, now the free rotation will stop and the rotation will become restricted, okay. And there is restricted rotation. So how they will be arranged now? Due to this steric repulsion between these bulky groups, the middle ring, if the middle phenyl ring is present in the vertical, if it is present in the vertical plane, then other will be in horizontal plane, okay. Horizontal, vertical, then horizontal. To minimize the repulsion, they will become out of plane, perpendicular to each other. So if I talk about the first and third ring, so first and third ring, they will be in the same plane. Middle one is having different plane, but the terminals are having same plane. Terminals are having same plane, that means they can show geometrical isomerism. And you can see these terminals are having different groups, okay, methyl bromine, methyl bromine. So yes, there can be geometrical isomers. When the methyls are present at the same side, this will be cis. When they are present opposite, then that will be trans. So we can say in this third one also, GI is possible, geometrical isomerism possible, okay. Now the fourth one, in the fourth one you can see you have double bonds. 1, 2, 3, 4, 5. 5 double bonds. This is an example of allene. 5 double bond means odd number of double bonds, okay. Odd number of double bonds. That means, suppose if this is horizontal, this will be vertical, then horizontal, then vertical, then horizontal, okay. So this one, this carbon and this carbon, last carbon, they will come in the same plane, okay. They are having the same plane, right? So their terminals are also having same plane. So here you have methyl and hydrogen, here you have fluorine and chlorine. So yes, geometrical isomerism is possible here, okay. So in the fourth one also, geometrical isomerism, GI is possible. GI is possible here, okay. So these are the examples for the geometrical isomers. Fine. Now let's see the second type of isomerism, stereoisomerism, that is optical isomerism. So what is optical isomerism or optical isomers? So optical isomers are the compounds which have same molecular and structural formula, but have different optical activity are known as optical isomers. Okay, they have same molecular formula, same structural formula, but their optical activity is different. Now the question is, what is optical activity? So optical activity is certain substances possess the property to rotate the plane of polarized light. Such substances are called as optically active substances, and this phenomena is called as optical activity. Okay, so plane polarized light is that light which vibrates, in which the waves vibrate in the same plane, okay, in one plane only. That is called as plane polarized light. So we have some substances, these substances have this property, they can rotate, they can deviate or rotate the plane polarized light, right? So these kind of substances are called as optically active. And on the other hand, the substances which cannot rotate this plane polarized light, they are called as optically inactive, right? And this phenomena is called as optical activity. Okay, so let's see. Now in optical isomerism also we have different categories of compounds, like first of all we have enantiomers. Now what are enantiomers? Enantiomers are those stereoisomers which are non-superimposable mirror images of each other. Okay, so these are the compounds, if you will take their mirror image, that mirror image will be non-superimposable on the other mirror structure or a mirror image of the compound. Okay, so two mirror images which are non-superimposable, they are called as enantiomers. Okay, enantiomers or enantiomorphs. For example, if we take the example here, in enantiomers there is the presence of chiral carbon. Chiral carbon is that carbon which is having 4 different groups. Okay, and if I make the proper tetrahedral structure for this chiral carbon, okay, so suppose you have one hydrogen, you have one methyl. Okay, now let's take one chlorine and let's take one fluorine. Okay, this is the compound, and here you can see on this carbon you have 4 different groups. So that's why this will be called as chiral carbon, which is represented by this asterisk mark. Okay, and if I take the mirror image of this compound, so the mirror image of this compound will be hydrogen, methyl, chlorine and fluorine. Okay, this is the mirror image of this compound, and if you will see, these two mirror images are non-superimposable on each other. They will not superimpose on each other completely. Okay, so that's why we can call them as enantiomers. Fine. Now the second category is diastereomers. Diastereomers, the optical isomers with or which are not mirror images to each other are called as diastereomers. Okay, so these diastereomers are not mirror images of each other. Okay, so for example, the geometrical isomers can be called as diastereomers. Geometrical isomers can be called as diastereomers. Why? Because geometrical isomers are not mirror images of each other. For example, if I take the very basic example, okay, this is the cis isomer. If I take the trans also, this is the trans. Okay, this is cis, this is trans. Okay, you can see that they are not mirror images to each other, so these can be called as diastereomers. Okay, so diastereomers might have chiral carbons also, but the two compounds is even after having the chiral carbons, if you will compare the two compounds, if they are not mirror images of each other, then you can call them as diastereomers. Okay, we can take one more example. We can take this Fisher formula here. Suppose you have this compound, okay, CH2OH. This is one compound, and if I take another one, Okay. Now, if you will see these two compounds, if you will compare these two compounds, they are having chiral carbons 1 and 2. In this one also they are having chiral carbons. But if you will compare these two, you can see that they are not mirror images of each other, because here the two OH groups are at the same side, whereas here they are opposite. So they are not mirror images of each other. That's why we can call them as diastereomers, right? Now, the third category is meso-isomers. So what are meso-isomer or meso compounds? So let's see. Achiral compounds which have chiral centers is called as meso compounds. So even after having the chiral carbons, they are achiral in nature. They are optically inactive. Why? They are achiral means their optical rotation is 0, and as their optical rotation is 0, why? Due to internal compensation of optical rotation. Now, what is this internal compensation? So let's take one example here. Okay, suppose we have this compound CH3, OH, H, OH, okay, and H. Okay, now if I talk about the chiral carbons, yes, this carbon is chiral, this carbon is also chiral, okay, but here plane of symmetry is present. Plane of symmetry is present here. Plane of symmetry is present, and due to this plane of symmetry, if this chiral carbon, suppose this chiral carbon is rotating the light right hand side or clockwise, okay, means dextro-rotatory, and the other chiral carbon is rotating the light anti-clockwise, levo-rotatory, then these two are going to cancel out their rotation internally. They are going to cancel out their rotations. Rotation of light internally. This is how, okay. So these rotations are opposite to each other. So in this compound only, internally the two rotations are cancelling out each other's effect, and that's why it is called as internal compensation, and due to this the compound becomes optically inactive or achiral, okay. So such kind of compounds are called as meso-isomers or meso compounds. Fine. Now let's see. Let's try to solve the question related to optical isomerism. Okay, so we have to identify relationship between the following molecules. Okay, so here you can see this is Newman projection given here. We have to find out the relationship between these two sets of molecules. So if we just look at the first one here, you can see that you have this carbon, front carbon. This is also the front carbon. It is having COOH, OH and H. Okay, similarly here carboxylic, H and OH. And at the back carbon, this is the back carbon. At the back carbon you have three hydrogen. Here also at the back carbon you have 3 hydrogens. Okay, so they are having same structure. Okay, they are having same structure. But if I just place a mirror over here, then you can see that these two are mirror images of each other. These two are exactly mirror images of each other, and these mirror images will be non-superimposable. The first carbon, this carbon will be a chiral carbon, because this is having 4 different groups. So whenever in a compound, when there is only one chiral carbon, that is definitely optically active. Okay, so these two are optically active and they are non-superimposable mirror images of each other. That's why we can say that these are enantiomers. These are enantiomers. Okay, so now let's see the second one. In the second one you have this C double bond O group. Okay, 6-membered ring. Here the methyl is backward, means away from observer, whereas the second methyl is towards the observer. Whereas this is in the second compound it is completely opposite. The C double bond O, this is as it is, because this C double bond O, this carbonyl group, here the carbon is sp2, so this is a planar molecule. This is a planar group. Okay, this carbon is planar, so it remains as it is. But the methyls, this methyl has come towards the observer, and the other one is away from observer. So now if I just place one mirror in front of this molecule, then I will get this compound, exactly this compound. So they are mirror images of each other, right? They are mirror images, and if you just place it over this compound, then they will not superimpose on each other, because this methyl is going away from observer, this is towards the observer, so they are not superimposing each other. Similarly, the second methyl also. So they are also non-superimposable mirror images of each other. That's why these are also enantiomers. These are also enantiomers, okay. Now the third category, the C option. Here if you will see, okay, we have 6-membered ring and these 2 methyl groups are towards the observer. In the second compound, one is toward the observer and the other is away from observer. So first of all, let's see, do we have any chiral carbon? So yes, this carbon is chiral, this is also chiral carbon, okay. Here also these 2 are chiral carbons. So orientation of one chiral carbon is as it is, but for the second it has changed. That means when such kind of compounds we have where the orientation of one chiral carbon is exactly same, but for the others it has changed, so these are called as diastereomers, because now they are not mirror images of each other, okay. So these 2 are diastereomers. Diastereomers or diastereoisomers, okay. Fine. Now the last one, okay. In the D option, if you will see, CH3SO, this group is as it is, okay. Ethyl is also exactly same. Hydrogen, methyl, hydrogen. So only the orientation of 2 groups has been changed, okay. This first part, upper part is as it is, ethyl is also as it is. Only the methyl and hydrogen, their position has been reverted, and that's why you will see that these are also not mirror images of each other, because the orientation of the sulfur, orientation of the groups and lone pair around the sulfur, this is exactly same. So these are not mirror images of each other. So that's why these are also diastereomers. These are also diastereomers, okay. So we have find out all the relations between these compounds, okay. Now let's see one more question. So the next question is, Newman projections P, Q, R, S are shown below, okay. Which one of the following options represents identical molecules? We have to find out that among all these 4 PQRS compounds, which are identical, okay. So options are P and Q, Q and S, Q and R, or R and S, okay. So we have to find out the identical molecules. So let's see, we have to basically first of all make their proper structure, okay. So fine, let's see, if I just make a normal structure of this compound, what is this compound? So let's see, this is the front carbon. So at front carbon we have 2 methyl and 1 ethyl, okay. So ethyl, I can represent the ethyl in this way, CH3CH2, and this is the carbon, this is the front carbon, and on this carbon you have 2 methyl also. So 1 methyl, second methyl, okay. So this is the front carbon having 2 methyl and 1 ethyl, right? Now the back carbon. At the back carbon we have 1 OH and 2 methyls, okay. 1 OH and 2 methyls. So if we'll just try to name this compound, what will be the name? This will be the principal carbon chain, okay. And here you have OH, so numbering will start from this carbon 1, 2, 3, 4, 5, okay. So what will be the name of this compound? It is 2,3,3 trimethyl. 2,3,3 trimethyl 2-pentanol. 2-pentanol, okay. This is the name of this first compound, fine. Now if we just talk about the Q compound, so this is the front carbon. This front carbon is having 1 H, 1 ethyl, and this is the third group, okay. So let's first draw the third group. So you have CH3 and 1 more CH3 and OH, right? Now this front carbon, and this front carbon is having one ethyl. So CH2, CH3, this is ethyl and one hydrogen. So this is the hydrogen, right? Now the back carbon is having two hydrogen and one methyl. This is the structure of Q. If we write the name of this Q compound, what will be the name? What will be the principal carbon chain? Starting from this end, because OH is present at the second carbon. So 1, 2, 3, 4, 5 or 1, 2, 3, 4, 5. So both chains are same. So we can take any one of these, right? So 1, 2, 3, 4, 5. What will be the name of this compound? So here you have methyl at second carbon and ethyl at the third carbon. So we can write 2-methyl, 3 ethyl, or we should write in the alphabetical order. So we can write 3 ethyl, 2-methyl, okay, 3 ethyl, 2-methyl and 2-pentanol. 2-pentanol, okay. This is the name of the Q compound, right? If we talk about the R compound, this R compound, this is the front carbon. So this is having 2-methyl and OH. So CH3, OH, okay, and then back carbon is having, this is the back carbon, this is having one hydrogen. So CH, okay, and two ethyls. So CH2, CH3 and CH2, CH3. These are the two ethyls. So let's write the name of this compound as well. So what will be the chain? This straight chain we can take, right? So 1, 2, 3, 4, 5. Here also you can see that these two are exactly same, okay. 3 ethyl, 2-methyl, 2-pentanol, okay. So let's write 3 ethyl, 2-methyl, 3 ethyl, 2-methyl, 2-pentanol. 2-pentanol, okay. So these Q and R, these two compounds are identical. These are exactly same, right? Now let's talk about the last one as well. This is the front carbon. So front carbon is having one methyl and two hydrogen. So CH3, CH2, okay. Now at the back carbon you have OH, ethyl and this isopropyl group. So this carbon is having OH, ethyl, CH2, CH3 and one isopropyl group. So CH, CH3, CH3. This is the structure of last compound. Now let's see which chain we can select. Okay. So 1, 2, 3, 4, 5. Okay. If we start from this 1, 2, 3, 4, this chain will be main chain, and 1, 2, 3, 4, 5. This will be the numbering, right? So what will be the name of this compound if we write? We have 2-methyl and 3-ethyl. This is same. So 3-ethyl, 2-methyl, okay. But you have OH group at third carbon. So we can write 3-pentanol. 3-pentanol. 3-pentanol, okay. Fine. So but S is different as Q with respect to Q and R, because it is 3-pentanol. These two are 2-pentanol, right? So only Q and R are identical. Fine. So what will be the answer of this question? Q and R, this is given in option C. So that's why here option C will be the right answer. Fine. So this is how you can solve the questions related to stereo-isomerism. Fine. So that's it from my side on this topic. We'll be continuing this series. So stay tuned with us and don't forget to watch the complete series. The link is given in the description box. Fine. And do share your queries and suggestions in the comment box, right? So I'll see you in the next video. Take care. Thank you.